Hey, good morning, everyone. Time for us to get started on our FRQ trainer for calculus yet again. We are on the graphs of a derivative problem, so let's continue with our work. So here we have another memorable scene in North by Northwest. Our Roger Thornhill is hanging off the side of the Mount Rushmore Memorial in South Dakota. Didn't write a whole lot about this here. We are still going to keep on going with the crop duster. This is pretty much the same setup as yesterday, but we'll just read through the problems. It's the same graph and everything. At what values of t does a crop duster turn around? Are there any points of inflection on the curve of the crop duster's position? B. What is a crop duster's furthest distance from the crossroads? Justify your answer. And C. Find the crop duster's average velocity on the interval from 0 to 40. Okay, so I see the word average there for letter C, and I know what that means in calculus. That's an integral expression. Furthest distance for letter B, that sounds an awful lot like we're going to be using a candidate test. We're trying to maximize the distance, of course. And here for letter A, we're taking a look at, well, to start off with, something's going to turn around whenever its velocity changes from negative to positive or from positive to negative. So that's what we're going to be looking for. I've highlighted different sections here, and I've called your attention to some points. The yellow section here. In the yellow section and the pink section, the velocity graph is above the x-axis. So in yellow and pink, the velocity is greater than 0. And kind of on that same token, blue and green represent areas where the velocity is less than 0. Okay, so we have above the axis, velocity is greater than 0. Below the axis, velocity is less than 0. Which means that if you are in either the yellow or the pink section, you are heading north because positive velocity is in the north direction as we have set up our problem. If you are on the blue or the green section, then you're heading south because you have negative velocity. Okay, now that we've said that, points 1 and 2 are special to us because at point 1 and 2, the velocity is either changing from positive to negative or from negative to positive. So at point 1, velocity is going from that positive in the yellow part to negative in the blue part. So that looks like it's going to be a relative maximum. Velocity changes from positive to negative. It's a relative maximum. That's also a place where the plane is going to turn around. And that relates nicely to point number 2, because point number 2 is in exactly the opposite situation. The green section to the left of point 2, we have a place where the velocity is negative. The pink section to the right of point 2, we have a place where the velocity is positive. So if the velocity changes from negative to positive, first of all, that's going to be a place where the plane turns around. So the plane turns around at point 2. And that's furthermore a relative minimum. What we've discussed so far is going to allow us to answer the first part of question A. So when does the crop duster turn around? At t equals 10, the velocity changes from positive to negative. Therefore, at t equals 10, the airplane changes direction from north to south. And then likewise, at t equals 24, the velocity changes from negative to positive. So the airplane changes direction from south to north. Let's take a look at what happens for the points of inflection. And well, a point of inflection is a place where the graph of the second derivative changes from positive to negative. What we're looking at is a graph of the first derivative. So what we're going to need to know is, when does the derivative of this graph change, either from positive to negative or from negative to positive? Since the derivative is the same thing as slope, the derivative of this graph is going to change either from negative to positive or from positive to negative whenever we have a relative extrema. So where do we have a relative extrema? And that is only at point 3. To illustrate that point even further, take a look at what happens at point 3. The slope of the velocity changes from negative in the blue section to positive in the green section. So the slope of the velocity graph is the second derivative of our position graph. So our position, logically, is going to change, or the second derivative of our position changes from negative to positive at point 3. And if I take a look at that closely, that is t equals 13. So now I think we're ready to answer the rest of part B. A point of inflection is a place where y double prime changes from positive to negative or negative to positive. And since y prime is equal to velocity, y double prime is equal to v prime, which is the slope of the graph. The slope of the graph changes from negative to positive at t equals 13. So therefore, the curve of the crop duster's position has a point of inflection at t equals 13. Moving on to letter B. What is a crop duster's furthest distance from the crossroads? Justify your answer. Well, first of all, we know that s prime is equal to the velocity of 0, or the velocity. And so the position has a critical number when the velocity is equal to 0. And the velocity equals 0, if you take a look at that graph, the velocity curve crosses the x-axis at t equals 10 and t equals 24. We talked about that at great length earlier. You can go ahead and look back at that graph. So at t equals 24, something that we also discussed earlier, that's a relative minimum because the velocity is changing from negative to positive. Therefore, s prime is changing from negative to positive. It is technically a relative minimum, and there is no need to test it. But if I was in your position, I would test it anyways. So the areas that we're going to look for is the following. From 0 to 10, remember at 10, the graph changes, or the graph crosses the x-axis. That area in that first triangle is 150. Let's take a look at the second triangle. The second triangle over here, maybe I should go up here. This second triangle here has a width, see this is going from, I think, 10 to 24, so that's a width of 14 and a height of 20. So that second rectangle has that second triangle has an area of 140. Of course, we're below the x-axis, so the integral is negative 140. And let's take a look at that last triangle. Right over here, that last triangle. Well, this goes from 24 to 40, so that's a base of 16. And this height, I believe, is 10. And yes, it is. It's 10. So the area of that third triangle is half of 16 times 10, which is just 80. Remember, area is the same thing as integral. Well, kind of, because we have to look at the pieces of area that are below and above the x-axis. Okay, so we have a way to calculate integrals. We have critical numbers, so we have everything we need for our candidate tests. Let's make our chart. So we have t, and then the well, this is actually, what are we calling this? This is position, right? So at t equals 0, the position is 20. You can see that a few ways. Firstly, they gave it to you. Secondly, if you substituted 20 into this integral expression right here, you get an integral from 0 to 0, which is 0. So that position is going to be 20. Right, next thing we're going to test is t equals 10. T equals 10, the integral is the integral, this integral right here becomes the integral from 0 to 10, and the integral from 0 to 10 is 150. So the position becomes 20 plus 150, which is 170. Next line. All right, this is a line that you actually didn't need because we already knew this was a relative minimum. But, you know, to be academic about it, the position at t equals 24 is 20, plus the integral from 0 to 24. The integral from 0 to 24 includes the positive area 150 and the negative area 140. So when you add that together, you get the position at t equals 24 is 30. Lastly, we need to find the position at t equals 40. So at t equals 40, very similar to what we did before, we're just going to add on a new bit of area. It's going to be 20, the initial position, plus the area from 0 to 10, which is 150, plus the area, or minus the area from 10 to 24, which is 140, and then plus the area from 24 to 40, which is 80. All of that gives us 110. Can you see which of those is maximum? Yeah, I think you can. That's at t equals 10. We've got a maximum distance of 170. This chart will also tell us that at t equals 0, we have our minimum distance from the crossroads, which is t equals 20. So it's time for us to summarize. Our summary should be, the crop duster's furthest distance from the crossroads is 170 feet. And if you want, you could say when t equals 10 seconds. Although that's definitely not necessary. No one's asking for that in the question. Did we justify our answer? And yeah, we did. We showed a lot of sound math here. We showed that we were using a candidate test. With that chart, you may want to write down candidate test so whoever's reading your paper knows what you did. Over here, maybe we can, you know, add maximum and minimum to the chart. There we go. Now we've labeled which ones are minimum and which ones are maximum for sure. And I can't think of anything else that we need to do. Maybe one thing we could do is say the position. What function is a position? S? I think S is a position. So we could have added ST equals. And that's it for letter B. Finally, we're going to go on to the average velocity. And it's the same old thing. I think we've done this practically every day that we've been doing FRQ trainers. But how do I find an average? The average of anything is its integral divided by the difference in time. So what is the integral from 0 to 40 then? Okay, so this is one place where I've seen students kind of not get this right. They like to put the 20 in there somewhere. But 20 doesn't have anything to do with the integral. 20 is the initial position, or maybe I should say the position when t equals 0. It's not really part of the area, so it's really not part of the integral. So I think you can leave the answer the way it looks here, but I'm just going to go ahead and simplify that a little bit. That's 90 over 40. And then, as is my instructions for you, write a small one-sentence summary. So on t to 0 to 40, the crop duster's average velocity is 2.25 feet per second. Naturally, you could have left that as 90 over 40 or 9 over 4. Anything that is equivalent to the correct answer will be considered correct. So if you, in the non-calculator section, and you don't want to, make a arithmetic error, don't make an arithmetic error. Just leave it as a fraction that is unsimplified. That brings us to graphs of a derivative. You can pause it here if you want to copy this down. But when you have the graphs of a derivative, you will have a direction change whenever the velocity is equal to 0. For most of these charts, that means when the velocity crosses the x-axis. I think there was a problem in the past where that wasn't true, and that's because they didn't give you the graph of the actual velocity. I think they gave you the graph of velocity plus 10 or something like that. But as long as you set the velocity equal to 0, you should be able to get this graph. So let's write the word usually. Okay. Because it has happened before and it could happen this year. If you need to evaluate an integral, a definite integral, it's just going to be the area between the curve and the x-axis. Don't go overboard with your calculus here. You shouldn't have to do a whole lot of integration analytically. Most of the time, especially if you're given the graph, just find the integral with the area. Average velocity is, the same average velocity or the same average formula that we've used for anything. And don't forget to use the fundamental theorem of calculus, especially if you see a difference between two functions. That is the fundamental theorem. While we're at it, we should mention that the other part of the fundamental theorem of calculus, which would be the derivative of an integral, don't forget that either. Okay, because that can be used, and I mention that because we are going to use that in the Check Your Understanding. Let's look at that Check Your Understanding now. We have a graph here, and I'm really sorry I did this because I chopped off a piece of this graph that you're going to need to know to answer this question. And that is g prime of x is equal to f of x. Don't worry, that should be fixed once we get the material in your hand. Part B. For the function g defined in part A, which is, of course, g prime equals f, find the x-coordinate of each point of inflection on the open interval and then explain your reasoning. So how do I find a point of inflection? Well, a point of inflection is any place where, or a point of inflection of g would be any place where g double prime changes from negative to positive and from positive to negative. Well, what is g double prime? Well, if g prime is f, that means that g double prime is f prime. And like we did earlier, that means that since f prime is the slope of the f curve, that means we'll have a point of inflection whenever the slope changes. Let's take a look at this curve. Is there any place where the slope changes either from positive to negative or from negative to positive? If you're looking at that relative maximum at 1, 2, you're correct. Okay, at x equals 1, the slope of f changes from positive to negative. Therefore, g of x has a point of inflection when x equals 1. Okay, and I think that's all we need. Did we explain our reasoning? Yeah, we did. Our reasoning has to do with the second derivative of g. Let's take a look at letter B now. Let h be the function, and I'm having trouble reading this. Let h be the function defined by h equals the integral from x to 3 of f of x dx. Oh, look at that. They're trying to fool you by putting the x as the lower limit. But there is a way to change it so that the x is on the upper limit. Hopefully you'll remember that. If not, take a second to think about it. Let's see. So find all the values in the closed interval from -4 to 3 for which h is equal to 0. Okay, when is h going to be equal to 0? Well, maybe the first thing we should think about is h is equal to that integral from x to 3, and that's just the area between some point x and 3. Okay, so we're looking at area. So if I'm taking a look and I want to find out when is that integral equal to 0, or h is going to be equal to 0 whenever that integral is going to be equal to 0. So the first and most obvious place where that integral is going to be 0 is going to be x equals 3. When x equals 3, the integral becomes the integral from 3 to 3, which everyone knows that's equal to 0. Now, second one, for the second one, we've got to find a place over here where the area is going to be 0. And if I take a look over here, this from 2 to 3, this is a triangle below the x-axis with a base of 1 and a height of 2. So this area here is 1, and the integral here is going to be -1. And then if I back it up just one more unit, this triangle right here is similar to this triangle. Actually, it's congruent to that triangle. It's got a height of 2 and a base of 1. So if I go from x equals 1 to x equals 3, those two triangle areas should cancel out. So we're going to look for areas of equal region, which we just did. And so that integral from 1 to 3 is going to be equal to 1 plus -1, which is equal to 0. So h of 1 is equal to 0. Is there any other place where that's going to happen? Backing it up, we know we got h equals 0 here. And then if we go back one more unit, this area here is 1. So you can count with me. 1 plus 1 plus -1, that's equal to, well, 1. And then if I back up again one more unit, this area down here is 1. So if I take the integral from -1 to 3, I'm going to get -1 plus 1 plus 1 plus -1, which conveniently is equal to 0. Okay. So h of -1 is also equal to 0. Therefore, h is equal to 0 whenever t equals -1, 1, or 3. Now you might ask yourself, why are there no more? And if you look at the graph here, everything to the left of x equals -1 is below the axis. So from -1 on to the left, we're just going to be adding a lot of negative area. So we're never going to get back to 0 again. Okay, so that's letter C. A little trickier than B, actually a lot trickier than B, but not so much if you understand that that integral is the same thing as area. Finally, we're ready for letter D. For the function h defined in C, find any intervals where h is decreasing. So first off, what does it mean in calculus if h is decreasing? Well, in calculus, h is decreasing when h prime is less than 0. Okay, so when is h prime less than 0? Well, first of all, what is h prime? H prime is just the derivative with respect to x of h, and h was defined by an integral expression. Now, it's difficult to take the derivative of an integral if the constant is in the upper limit and the variable is in the lower limit. So like I was alluding to earlier, we're going to switch the upper and lower limit and add a negative sign right here. There's my negative sign. And that's going to make this so I can take the derivative really easily, because the derivative of an integral with a constant lower bound and a variable upper bound is just the integrand. So the derivative of the integral is just negative f of x. So when is negative f of x less than 0? Do a little bit of algebraic, algebra. What am I saying? Do a little bit of algebra here, and you'll see that this is the same thing as when is f of x equals 0? When is f of x greater than 0? So all you got to do now is figure out when is f of x greater than 0. When is the curve of f above the x-axis? And I think you can see it. F of x is greater than 0 when x is between 0 and 2. So if x is between 0 and 2, f of x is greater than 0, so negative f of x is less than 0, so h prime is less than 0, therefore h is decreasing. You kind of unwind that logic backwards. Therefore, h is decreasing when x is between 0 and 2. Okay, everyone, that's the end of our second day of graphs of the derivative. These problems are never, I shouldn't say never, but usually to do these problems, you'll just have to have a firm understanding about the way that the graph of a derivative works. And once you can get that, you'll be able to gather most of the points in these sections, barring a left turn or a curveball thrown by the College Board, which is totally possible, but it's not your job to get every point. It's your job to get as many points as you can. So, that said, I'll see you guys later, and have a good rest of your day.